Welcome. Hope you had a great weekend. I got some exciting news, I guess exciting for me at least, that we are now in review. The College Board came out and said, hey, guess what? Last two units, 7 and 8, don't even worry about it. I mean, maybe it's 8 and 9 for chemistry, I forget. So you did some great work last week, and we did some buffers, acids work, and not going to be on the test. So, congratulations, you guys. Learning more than you need to, I suppose. So we're going to review, and here's the list of Unit 1 stuff. I feel like we did this like a month ago. Maybe we did. So hopefully it'll be come back to you quick, be easy. And so the first thing is the mole. Molar mass. Honestly, if you don't know molar mass at this point, you can get out of the classroom. Yep, I hear you laughing already. Now, the mole is 6.02 times 10 to the 23rd. You can use it to get the amount of substance, the number of particles, it's related to the mass, etc. But the mass of a substance, remember, the mass spectra, we use the atomic mass, which is the weighted average of the isotopes. And the abundance, the relative abundance, and the weighted average. So here we have a graph, the mass spectrograph. I have a feeling the College Board's going to throw something like this at you. Where you have, again, I don't know. This bothers me that the proportions here don't add up, but whatever. Just ignore that. So you could get, there are two isotopes of this element, and its mass is going to be between 10 and 11. A lot closer to 11 than 10, but it's going to be a little lower than 11 because there's the 10 isotope. And here's another one where we have isotopes from 196 to 204, and we've got 1, 2, 3, 4, 5, 6, 7 isotopes. The mass on this one, a little trickier. It looks like it's probably going to be around 201-ish, 200, somewhere in here. So you have that big peak at 202. It's going to be balanced by 200, but it's also going to be pulled down by these. Obviously, you're not doing calculations unless you have more information specifically. And this, if you have 6 or 7 isotopes, that calculation is going to take too long for like a 45-minute test. So something like this is more likely. You can also use this to figure out what element it is. I don't think I have the... skip down here. Come on. So again, you would look at the masses, and borons are like 10.81, so that'd be a good one for the slide right here. So that's mass spectra. Let's see how I'm doing here on the review. This is all the stuff from Unit 1. Pure substances and mixtures. We can do that next. Mixtures and pure substances. This is kind of a blurry picture, but I liked it. So you have matter up here, and you have a pure substance, 100%. It can be a compound, it can be an element, and the pure substance is going to be, if it's an element, you're going to have like hydrogen or oxygen there. The compound is going to be some combination of those two. And again, that can be ionic, can be covalent. Mixtures are not going to be just one substance. They're going to have different things mixed in. Mixture. They can be uniform. They can be there can be a separation there. One thing with the mixtures is purity, even within the mixtures. Or if you have a mixture of different things, and there can be an impurity that's going to throw off any kind of analytical measurement of that substance. All right, so not too bad. If there's anything on this, it'll be like one question. All right, atomic structure. Again, I'm spinning wheels here. Things that we learned about a couple years ago. At this point, should be pretty well solidified in your brains, right? In the center of the atom, we have the nucleus, which is made up of the protons and the neutrons. And flying around the nucleus, we have the electrons, which are in these shells. And these shells do have shapes. Anyway, the charge of the protons +1, charge of the electrons -1. Neutrons, no charge. That's probably not going to be on the test, but remember the neutron is a proton and electron smashed together. The massive part of the atom is in the nucleus, and the electrons have are considered massless, even though they have a mass. I believe that should be 1/1800. They rounded up, just being a nerd. Anyhow, as we go out from the nucleus, right, that potential energy increases from the electrons. These outer electrons are valence electrons. We want the magic number is 8. And you can get that number based on the periodic table. Again, that should be second nature at this point. The outer electrons here will be shielded from the nucleus by the inner electrons. So keep that in mind, that is going to decrease the attractions to the nucleus as we expand outward from the atom. We have Coulomb's law, which is all related to this. All right, the force is equal to a constant times Q1 times Q2 all over R squared. So the charge of attraction or repulsion of a molecule of a substance is due to the size. Right, it's a +1, +2, +3, -1, -2, -3. Right, the size of the charge, and it's also related to the distance that they are apart. The further apart they are, the less they're going to feel the attractive force. So if we go back here, I have an electron way out here. It's not going to feel the force of the nucleus, the positive nucleus, as much as the electrons that are here. The distance is much closer. So there's going to be a greater attraction for the inner electrons versus the outer electrons. All right. And then we look at the periodic table. We can look at the trends. I'll probably save that one for tomorrow. But we look at the periodic table. Again, group 1, 1 valence electron +1 ion. Group 2, 2 valence electrons +2, and that's +3. Don't usually form ions, -3, -2, -1, and the noble gases, which have that electron configuration of 8. Atomic radius, it's the configuration of the periodic table. Right, as we go across, we're always adding an electron. Right, so 1 electron, 2 electrons, 3, 4, 5, 6, 7, 8, 9, 10. All right, as we go down, we're adding layers, keep in mind. So if I have first layer here, this row is going to start the second layer, and then we'll have 3 layers for these elements, 4 layers for these elements, and so on. But with atomic radius, which is the trend, as we go down, they are going to naturally get bigger because I'm adding an entire new layer. So 1 layer, 2 layers, 3 layers, 4 layers, 5 layers. That makes sense. As I go left to right on the periodic table, the elements counterintuitively increase in size as we go towards the left-hand side. So going left, the elements increase. Even though I'm adding more protons and more electrons going across, they do decrease going from hydrogen to helium or lithium to neon. They decrease because as I add those protons and electrons, what I'm doing is I'm increasing my charges, right? So this Q1 and Q2 are increasing from Coulomb's law. And as that happens, the force of attraction between the electrons, right, that I'm adding in the same area is being more attracted to the nucleus, just slightly. So as I add an electron here, I add 1 proton here, that increases the Q. That increases the Q out here. So my force of attraction is greater. So to recap, the atomic radius increases as we go down, and it increases as we go from right to left on the periodic table. So neon, smaller than lithium. Neon, smaller than sodium. Lithium is larger than beryllium. All right, 10 minutes of review. I'm going to have you do some problems. Enjoy.